So let us continue with our study of the basic properties of the elementary measure. But before we do that, I would like to state an easy observation, or you can state it as a lemma. It is that if E and F are elementary sets, then E union F is an elementary set, E set minus F is an elementary set, and E translated by an element X for X in Rn. So let us suppose that we are in Rn. So if you translate it by a vector X in Rn, then this is also elementary. This we have already seen before, but let us review it here. Now the proof is quite easy. So for the first part, so let me put numbers here. So for the first part, it's very easy. If you write E as a union of boxes, disjoint or non-disjoint boxes Bi, I equal to 1 to n, F is a union j equal to 1 to m Bj prime, then E union F is simply the union of the two things, I equal to 1 to n union j equal to 1 to m Bj prime, and it is obvious that this is a union, finite union. This is a finite union of boxes in Rn. So all these Bi's and Bj primes, Bi, Bj prime belong to Rn for Ij for each Ij. Yeah. So it's quite obvious that the union of two elementary sets is elementary. Now let's come to the second one, E set minus F. So now let us again assume that E is a union of Bi's, I equal to 1 to n, and F is a union j equal to 1 to m of Bj primes. So again Bi's or Bj primes are boxes in Rn. Then the set minus is simply E intersection by F, the complement of F. So you can write it as follows. So this is, the first one is simply the union of Bi's intersection with the union of j equal to 1 to m Bj prime complement. So now you can use De Morgan's law. So you will get here j equal to 1 to m Bj prime complement. So we have union I equal to 1 to n Bi intersection with this intersections of Bj prime complement. So we have the union over these kinds of sets. So let me call it Ci. So if we show that each Ci is an elementary set, then we are done, due to the first property of union of elementary sets being elementary, due to the first property. So now let's try to show that each of these Ci's are elementary, and we will do an induction on the number of on the number of boxes that are used to define F, the elementary set F. So, here we have defined F as the union of Bj primes over m sets Bj prime. So, if we can do an induction on M and show that for each M this is an elementary set, then we are done, because then we will have a finite union of elementary sets which is elementary. So, let us try to do that. So, to prove that if B is a box, then B intersection j equal to 1 to m Bj prime complement, this is a complement here, is elementary. So, this is what we have to show for any box B. So, first take m equal to 1. So, this will be our base case, this is our base case for the induction. So, to show that for m equal to 1, so suppose that we take B1 prime is a box. So, let B1 prime be a box, then we have to show that B intersection B1 prime complement is elementary. Okay. So, what we are going to do is to break it up into coordinates, and we will see what happens for each coordinate. So, remember that B is a box. So, it is a Cartesian product of intervals. So, each I k is a subset of R, is an interval, bounded interval in R for each k. And similarly, B1 prime is a box. So, this is a Cartesian product of, let us say, J1, J2 cross Jn, and again Jk is an interval for each k. Now, we have to use some formula which describes the complement of a Cartesian product of n sets in terms of the complement of the individual coordinates sets. So, I want to write down a formula for B1 complement, and this is as follows. So, first you will have union I equal to 1. So, let me go to a new page. So, B1 complement, B1 prime complement, this is equal to, first you will have a union I from 1 to n, J1 cross, you take the complement for the jth interval, and I varies from 1 to n. So, this is a union of n sets with the ith set having the ith coordinate with a complement. Then again we have, so union, so this is one component. Then we have a union over I and j. So, now you will have two coordinates with complements, J1 cross, so I not equal to j, J1 cross Ji cross j j. So now we will put a complement over these two indices and the rest remain the same. So here we are assuming I not equal to j, because if I equal to j then you will just have one set. So this is for distinct coordinates I and j, and you will put a complement for each of the coordinates j I and j j. Now we have other similarly for I j k 1 to n, I not equal to j not equal to k. So this formula is a bit tedious and might look scary, but the idea is very simple, and it just uses the elementary operations of unions and complements and cross products of Cartesian products. So if you I suggest you to go back and check what are the formulas when you have the Cartesian product of a union or the union of Cartesian products and so on, and then what happens when you take the complements for such unions. So in the third step we will have j1 cross so now we will have three coordinates with the complement j complement and j k complement, and the rest are the same. And similarly in the end, so you will have many unions, and in the end you have the union of the set j1 complement cross j2 complement cross jn complement. So here all the n coordinates are with a complement here. So this is a big formula, but all are so at each step you are taking a union. So here this is a union, this is a union, this is a union, and so on. All these are unions. So when we take the intersection of all this, of the huge thing with our box, so this is our box B, then you can distribute it, distribute this Cartesian product inside the unions, and then you will have an intersection of two Cartesian products, and then again you can distribute it. So let's write this down carefully. So let's write this down carefully. So you have union I, so this is I am computing B intersection B1 complement. Okay. So this is I from 1 to n j1 complement, the complement should be on the ith, ji complement cross jn, okay, and this whole thing is intersected with I1 cross In. So even you can take this inside this union. So I can put here this intersection and followed by a union. Similarly, then you have union I j from 1 to n, I not equal to j, and again you have j1 cross ji complement cross j complement cross so jn, and again you have an intersection with I1 cross In. So this is the second one. Then you have again a union with I j k from 1 to n, I not equal to j not equal to k, and here we have complements on 3 coordinates I j k, cross Jn, and you have again an intersection with I1 cross In. And similarly you continue like this, and in the end you will have another union where you have the complement on each coordinate Jn intersected with I1 cross I2 cross In. So you have for each of these an intersection of two sets, each of which are Cartesian products themselves. So let's consider, for example, unions from the first group. Let's call this set A1. So our A1 is a union I equal to 1 to n J1 Ji complement Jn intersection with I1 In. So this is just by the property of cross products and intersections. This is simply J1 intersection I1 cross J2 intersection I2 cross Ji complement intersection II cross up to Jn intersection In. So now we have a finite union of such elements. So if we can prove that all of these are all these sets are boxes, then we'll be done, because then A1 will be an elementary set. And similarly one could do for other groups where you have 2 complements, 3 complements or n complements, and they will be all of the same form. So the idea is to show that if you have 2 intervals, of course their intersection can either be empty or it will be another interval. So intersection of 2 intervals is an interval. If you can show that intersection of the complement of an interval, so this is a intersection. If you can show that intersection of the complement of an interval with another interval is also an interval, then we would be done, because then it will be a Cartesian product of intervals, and so it will be a box. So it suffices to show that if I and j are intervals in R now, then I intersection j complement is also an interval. So this is again quite easy, and I leave it to you as an exercise. Check that this claim holds. So for example, I'll just give a visual idea. So if you have, this is I from A to B, and you have J from C to D like this. So this is J. Then I intersection J complement. So what's J complement? J complement is the area, is the region left of C and right of D. So I intersection J complement is simply the region from A to C. So similarly you can check all other cases. If I and j are disjoint intervals, then I intersection j complement will simply be I, and in all other cases as well, I intersection j complement will be an interval. So it's very easy to prove. So I leave it as an exercise for you. So therefore we have that all the constituent sets in the union of A1 is given by boxes. So each one is a box. Therefore A1 is an elementary set because it's a finite union. It's a finite union of boxes. Now we can go back to the other groups A2, A3 and so on, AN, and for each of these, because you have the intersection coordinate wise, therefore each one will be an interval and each of these constituent sets will be a box, and therefore you will have a finite union of boxes, and therefore for all these you will have finite unions of boxes. In particular, AN itself is a box because you have just one, so this is a box, and therefore we have proved that B intersection B1 complement is an elementary set. So this implies that B intersection B1 complement, B1 prime complement is an elementary set. So this proves the base case for our induction. Now we come at the induction step. This is the induction step, which is that assume that if B j prime j equal to 1 to m are boxes, then B intersection Bj prime, intersection of these Bj primes complement Bj prime complement j equal to 1 to m, this is an elementary set, and we will have to prove that if Bj prime j equal to 1 to m plus 1 are boxes, then B intersection of these Bj prime complement j equal to 1 to m plus 1 is an elementary set. So this will prove our induction hypothesis. So let's write down what is B intersection of j to m plus 1 Bj prime complement. Note that you can take out m of these and plug and group it with B. So this is B intersection j equal to 1 to m B j prime complement, and then again you can take an intersection with B m plus 1 prime complement. Now we know that from our induction hypothesis this is an elementary set. So this is in fact a union, let's call it K from 1 to L, CL intersection B m plus 1 prime complement, where each CL is a box. Because this is an elementary set, it is a finite union of boxes CL, K equal to 1 to L, and now we have to take this intersection with the B prime m plus 1 complement. So now we can distribute it inside the union, this implies that B intersection of j equal to 1 to m plus 1 bj prime complement is equal to union k equal to 1 to L C k intersection B prime m plus 1 complement. So we have just distributing the intersection inside the union, and now this is a box and this is a box. So we have already proved from the base case m equal to 1, we know that for each k, Ck intersection B prime m plus 1 complement is an elementary set. So we have already shown this. Therefore, now we have again a finite union of elementary sets. This implies that B intersection of m plus 1 bj prime complement is an elementary set. So now this completes our proof, because this implies that if E is union I equal to 1 to n bj and F equals union j equal to 1 to m bj prime, sorry, this is bi bj prime, then E intersection F complement is simply union I equal to 1 to n bi intersection of intersection j equal to 1 to m bj prime complement, and each of these is elementary. So this is E intersection F complement is elementary.